In this BME 3300 lecture, we're going to be talking about common mode rejection ratio, which is a strategy to eliminate common mode noise by differential amplification. So let's set up some ground rules as to when we can use differential amplification to eliminate noise. So first, if noise is common to both the terminals of our device, that is, if the same voltage appears on both terminals of the device relative to ground, and if what we care about is the difference between the signals on those terminals, that is, if the physiological signal that we actually care about measuring it can be obtained by subtracting the signals on the two terminals, which happens in a surprising number of situations, then we can remove the noise via differential amplification. So we're going to use the example of ECGs throughout this lecture to introduce this topic. So let's say we have the following situation. We are measuring an ECG. Here's a little man. He has a heart. He's got two ECG leads on him. ECG lead 1 and ECG lead 2. And we're getting signals from both of these. So let's say that the signal that we're trying to measure, the heartbeat or the ECG trace that we're trying to measure, lives between 0.1 hertz, a tenth of a hertz, up to about 100 hertz, and has an RMS amplitude of about 10 millivolts. On the other hand, let's say that the noise is mostly 60 hertz noise, which is realistic. It's mostly 60 hertz noise in practice. And it has a much, much larger 3 volt RMS amplitude. So the RMS here is really, really terrible. It's only 3 times 10 to the minus third. Clearly not a workable SNR. A notch filter, on the one hand, would remove signal. Right? We have noise only at one frequency, so you might think we could just use a notch filter, but that would remove signal because our signal goes through 60 hertz, right? It's possible to have large signal components at 60 hertz, where the noise is. So if we applied a notch filter, we would also remove signal. Now, as electrical activity moves through the heart, the voltage between 1 and 2, the probes 1 and 2, will change, but the noise is the same on those two probes. So that suggests that we can use differential amplification to remove it. So what we're going to do is we're going to use a differential amplifier to subtract the signals and eliminate the noise. So we're going to have this kind of situation. We're going to have our two signals, the voltage 1 from the first electrode. That will have this 3 volt 60 hertz noise signal on it. And let's say it has the negative half of the ECG signal on it. And let's say that the second electrode has the same noise because electromagnetically they're in the same, hertz here, they're in the same location, very similar location, so they're going to pick up pretty much the same 60 hertz noise with the same amplitude. We're going to put them into a box here. In that box, if it subtracts these two signals, if it takes V2 minus V1, V2 minus V1, then what will come out is just ECG. Right? You can see that if you subtract the two signals, then you're going to get rid of the 3 volt signal, or you're going to get the full ECG signal. So this device here is going to be the differential amplifier. So let's recall the differential amplifier topology. What we're going to have here is two inputs. Then there are two input resistors, a feedback resistor, this ground resistor, and the second input resistor. Then we have V out, so we'll call the feedback resistor R sub F, the top input resistor R1, and the bottom input resistor R2. To these we connect the voltages V1 and V2, which are respectively connected to the electrodes around the patient's heart. Oops. Like the electrode on the patient. Okay, So the equation for this amplifier we've also seen before, and that is that V out is equal to, in general, here accounting for the possibility that we don't have matched resistor ratios, in general it's equal to this Rg over R2 plus Rg times Rf over R1 plus 1 times V2 minus Rf over R1 times V1. And as we saw in a previous lecture, if the resistor ratios match, then this can be simplified down considerably to Rf over R1 times V2 minus V1. And specifically, what I mean is if they match, then we have the situation Rf over R1 is equal to Rg over R2. Okay, so going back to our example, if the ratios match, then we have that V out is equal to Rf over R1 times the 3 volt noise source, and let's say that that is mathematically equal to 3 times sine of 2 pi times 60, just arbitrarily making a mathematical form here, plus the ECG signal over 2, plus 3 times sine, minus, if we plug these in, then we have the difference between the two signals. And it's going to be, the second one is going to be 3 times sine of 2 pi times 60t, that's the 60 hertz noise again, minus ECG over 2. And you can see that these guys are going to cancel out. It's going to become a plus, and we're going to end up with Rf over R1 times ECG, the signal that we want. Okay, so it seems pretty simple, right? But in practice, there are actually 3 practical problems that can make this complicated to realize. This differential amplification difficult to realize. And the first problem is that in reality, op-amps have some common mode gain. And I'll illustrate what we mean by that. That is, the devices themselves will have some common mode gain, where we typically assume that it's 0 in analyzing the circuits. So an op-amp has this circuit schematic. You have some voltage V out, and then you have the voltages on the 2 terminals V minus and V plus. Now with these definitions, ideally V out is equal to the scalar A times the difference of the 2 signals, V plus minus V minus, where A here is the open loop gain and we assume that A is equal to infinity. It drives up the output voltage until at least you hit the voltage rails of the op-amp. But in reality, a more realistic equation is that yes, we have this large open loop gain that multiplies the difference of the 2 input signals. Sorry, that should be a V minus. But at the same time, we also have this non-negligible common mode gain, A sub Cm, that scales up the sum of the 2 signals. Right? So if we have the same noise source, for example, on V1 and V2, they would be canceled in this part of the equation, right, because we'd be subtracting them out, but they would actually be summed together in this part, and then scaled by this common mode gain A sub Cm. So again, A sub Cm stands for common mode gain. So a really great op-amp will have the open loop gain much, much larger than the common mode gain. And there's a quality metric that has been developed over the years to indicate the relative size of these 2 gains. And that is called CMRR, which stands for common mode rejection ratio. And CMRR mathematically is a logarithmic metric, and it's defined as 20 log 10 of the amplitude of the ratio of A divided by A sub Cm just to take care in case one of them is a negative gain. We have the amplitude there. And what we would like to have is that CMRR is as large as possible, but of course a very high CMRR op-amp costs quite a bit more than a low CMRR one. For example, one that's about 100 dB could be on the order of about $100. Okay, so let's go through an exercise to show how we can leverage the CMRR number for a given device in a useful way. So let's say that we have 5 volts RMS of common mode noise and a 10 volt RMS signal. Let's say then that we want to scale that 10 volt RMS signal so that it becomes 1 volt RMS at the output of the circuit. Now let's say then that in building that differential circuit we have an 80 dB CMRR amplifier, and the question is, what is the SNR of the output? Okay, so here I've given again the definition of CMRR. So what we can do right away is that we can define the open loop gain here. And that guy is going to be equal to 100, which we get from the fact that we want an output amplitude of 1 volt where the input is 10 millivolts. Right? If you divide the two, you get 100. So that means that 80 dB is going to be equal to 20 times log 10 of 100 divided by ACM, the unknown common mode gain. So we need to solve for that so that we can figure out what the SNR of the output is going to be. So we can convert 80 dB back to linear units, convert both sides back to linear units, and what we would get is that 80 dB is equal to 10,000. And then when we do this, we get rid of the 20 log 10 on the right-hand side. And then if we solve this, we get that the common mode gain is equal to 10 to the minus second, 10 to the minus 2. So that means that the noise at the output is going to be scaled by 10 to the minus 2 compared to what it is at the input. So up here, I defined the noise as being 5 volts RMS. So if we multiply that by 10 to the minus 2, we get the NRMS, the noise RMS, at the output is going to be equal to 0.05 volts. And because we said that we were going to have 1 volt RMS of signal at the output, now we can calculate SNR because we know both. So the SNR is going to be 1 volt of signal RMS divided by 0.05 volts noise RMS, which is equal to 20. So one practical problem was common mode gain of the device. Another problem is imperfect resistors. And this is one you'll deal with directly in the lab. So remember that we get a perfect differential amplifier only if the resistor ratios match. That is, if the ratio Rg over R2 is exactly equal to Rf over R1. But resistors are usually manufactured to only plus or minus 5% or plus or minus 10% of the value that they report on their stripes. So for example, a 1 kilo ohm resistor, a very common value, could actually have a resistance anywhere between 950 ohms and 1050 ohms. And if the ratios don't match as a result of these imperfect resistor values, we're going to get some common mode noise at the output, and we may also attenuate the output signal as well, compared to what we would like it to be amplified to. So thus it's essential to verify resistors with an ohm meter in hand so that we can get as close as possible. Of course, resistance also varies with temperature, and so modern instrumentation amplifiers will have some kind of temperature compensation. Now, errors in the resistor ratios, and indeed errors also just that are due to imperfect op-amp, can be compensated using a potentiometer. And I'm not sure if you guys have seen this. Sorry, I should stop talking when I'm writing. Potentiometer. I'm not sure if you guys have seen this before, so I'll show you what it is here. A potentiometer is essentially a variable voltage divider. It's a mechanically variable voltage divider. And it's represented by this kind of drawing in a schematic. So it looks like a resistor within an arrow coming off the side. And what this is illustrating is that the user can move this arrow up or down to tap into the resistor at any point along its length. So mathematically, what this is equal to is two series resistors. There's a voltage divider that is variable. And let's say that we have a 500 ohm potentiometer. And what we would have here is some x times 500 on the top leg and 1 minus x on the bottom leg. And then the output would be taken between those two. And x is some number that's going to be between 0 and 1, depending on how much you've turned the potentiometer. So that's the user mechanically set variable. And what we do to use a potentiometer is we insert it in a differential amplifier like this. We have the VA and VB signals. They're connected to the input resistors, right? It's almost the same here, at least in the top leg. There are multiple ways you can integrate this. There are multiple ways we can integrate this into a differential amplifier circuit. Multiple places you can integrate it. But one of the most sensible places is to put it here between R2 and the ground. So there's V out. Let's give some real numbers. We'd have 150K, for example, 1K, 1K, 150K, and then a 500 ohm potentiometer. That could help us, and we can, by changing the position of the tap along the length of the potentiometer, we assign more or less resistance over to the 1K resistor or to the 150K resistor. And we can tune it so that we can get an optimal ratio. So the procedure to tune this, as you'll actually practice in the ECG lab, is going to be to connect VA and VB to the same signal source. Right? So you take one signal source out of your signal generator that you guys used in the first lab, and you'd connect it to both VA and VB in this circuit, and then you would connect V out to an oscilloscope, and you would manually adjust with a screwdriver your potentiometer until the output signal is minimized. That is, until you see no signal variation on the scope. So now we're at the third problem, and the third problem is low input impedance. So again, I'll draw a differential amplifier, just so that we're on the same page about what I'm talking about in the topology. So now we have, let's say we still have R2 and RG here as before. Now the impedance looking into the V2 port, here's the V2 port, right, where we connect signal V2. The impedance looking into this port is only going to be determined by R2 and RG, right, since we assume that no current flows into the positive terminal of the op-amp. So that means that effectively this leg is disconnected and we just have this resistance looking into this terminal. So it's just going to be R2 plus RG, which is definitely going to be considerably less than the ideal infinity that we would have, that we would like to connect the transducer to so that we draw no current from it. Fortunately, it's pretty obvious how to address this problem, and we can do this by increasing the input. We can increase the input impedance to reduce the current draw by adding buffers to the inputs, or voltage follower circuits, which we've seen before. So what we would do here is we would connect a voltage follower to both the V1 and the V2 inputs of the differential amplifier. Oh, sorry. Okay, and now we've got V1 and V2 going into the buffers before they hit the differential amplifier. And this way, the transducers will see a very high input impedance. For example, the 741 op amp that we'll use in the lab will have a resistive input of about a mega ohm. On the other hand, the LF356 op amp is a bit more expensive one. We also have a bunch of those though. And the input impedance of that guy is 10 to the 17th, 11 orders of magnitude higher. Both of these numbers are typically going to be considerably higher than the combination R2 plus RG that we had on the previous slide. So let's return now to our touchstone ECG example. So overall, what our circuit should do is it should be differential, right? It should take the difference of the signals on the two ECG leads. It should have buffered inputs so as to reduce or minimize the current draw. It should have carefully chosen resistors to get really good CMRR. And something we didn't talk about here, but is that I did mention that, that these devices will be sensitive to temperature. And so one thing you can do for that is you can mount the circuit on silicon to minimize the temperature drift. Now, instrumentation amplifiers that you can buy commercially have all these characteristics. So let's put together all these circuits that we've just learned about in order to represent a modern instrumentation amplifier. So on the input, as we had before, we will have buffers. Then we'll have our differential amplifier stage right after that. Then after that, we'll typically have a cascaded low-pass filter and high-pass filter. So here's the low-pass filter component, illustrated first. And then we have the high-pass filter second, though it shouldn't matter. So, again, we have the buffers here. Then we have the differential amplifier. Then we have a low-pass filter. And the low-pass filter is used to weed out noise that's over about 100 Hertz for an ECG amp. And the high-pass filter here will be used to remove DC offsets and drift, very slow drift. Okay. Now, commercial instrumentation amplifiers will have selectable, though not usually finely tunable, gains. That is, you can select gain from among you can select the gain based on the circuit design from among a set of fixed finite gains, a finite list of gains. They'll have very high common mode rejection ratio, and they'll have some form of temperature compensation circuit and also be mounted on silicon. So almost every system that's used to measure electrical signals from the body uses some form of this design, coupling some kind of high input impedance stage with a differential amplification stage, and then a series of filters. So let's summarize what we've talked about in this lecture. First, we talked about common mode rejection ratio, which is a measure of how well common mode noise, that is noise that has the same amplitude on both ports of a transducer, how well that noise is eliminated at the output of an amplification circuit, specifically a differential amplification circuit. Then we talked about practical issues with differential amplification that we'll run into in building instrumentation amplifiers. And these are finite op-amp CMRR, resistor ratios that are not perfect and that do not match perfectly, and low input impedance. And we talked about strategies to deal with each of these. Then we talked about the features and the layout of instrumentation amplifiers.